You everyone for joining us this afternoon, I guess, Eastern Time. And I'm representing our authors. Miss Annie Price gave this talk at IAC in Paris 2 years ago. So why do you want to go to Titan? Well, it's a very exciting destination. It's got a dense atmosphere and low radiation. So if you can get there, people could actually live on the surface or in habitats on the surface. Of course, you have to get there fast, and that's what we're going to talk about a bit. The underground oceans might have life. Now, we had some exploration of Titan already. Huygens landed on Titan, got really good scientific information. And the NASA Dragonfly, which is shown to your right, which is a helicopter, is going to fly there in the near future, and it's going to be able to explore a small region. So the Titan aircraft is a little bit different. It's going to have would have a nuclear fusion power plant, and that's very exciting in and of itself. But it'll be able to go all over the surface and operate for many, many years and do things that smaller spacecraft like the Dragonfly can't do because they're very power limited. And this is less power limited. Many years ago, NASA did the Jupiter Icy Moon Orbiter mission design, and there they had a spacecraft with 100 kilowatts electric, and the scientists came up with all sorts of new instruments that they could only do with that amount of power. So that's what we're going to talk about today. This is the aircraft that was designed by Annie Price. It ended up being a turbofan, and I'll talk about, well, not really a turbofan, propeller aircraft, and I'll talk about that in a moment. But first, this is an experimental reactor. It's not really a reactor, it's a plasma experiment. It has very low magnetic fields, and we'll talk about why that's important. But it's used to demonstrate that the physics works for this particular fusion concept. And you'll learn about it more, but it is being run. It's been run for a year. Dr. Sam Cohen of Plasma Physics Lab is the inventor of it. And it's been supported by the U.S. Department of Energy and also by NASA. So here's the mission plan. You need a plan. Any kind of mission has a plan. So the first thing we do is spiral out of Earth orbit. And that's the way you get out of a planetary orbit if you have low thrust. Then we do a long transfer to Saturn. That hopefully won't take that long, and you'll see in a moment. Then we have to enter the Saturn orbit. So now we're in orbit around Saturn. Then we eventually encounter Titan and do orbit entry there. And then at that point, the aircraft detaches from the transfer vehicle and enters the atmosphere. And the engines themselves are covered when we're entering because it's hot. And then we uncover them at subsonic speeds, and then we start flying. We would land first to check everything out, and then it would fly around. Titan, one of the interesting things, of course, is all ice on Titan. So that's one of the things that drove us to propellers as opposed to some sort of jet engine. So here are the two major vehicles. On the left is the transfer vehicle. The yellowish objects are the fuel tanks. The black objects on the back of it are radiators. You need a lot of radiators because you always have waste heat. You can see the one engine at the end. On the front is just a generic transfer vehicle. And we don't show the aircraft on top of it in this particular picture. The aircraft, again, developed by Annie Price, is on the right. And it has 6 ducted fans. It has a reactor. Now, it's interesting because in the vehicle on the left, the reactor is used as a rocket engine, but it can also be used as a fusion power plant, which we're doing on the right. And the actual numbers we use for the delta V were done by our colleagues, Ghagheri and et al., on their own paper on a Titan mission using direct fusion drive. Direct fusion drive is the name we use for our rocket engine. It's used for other propulsion systems too, so it's not like exactly only ours. So here's the optimal landing. Now, this was an interesting work because at first we said, oh, we're going to have to use the fusion engine as a ramjet at high altitude. And that was made, we'd end up with a ramjet turbojet, but quite complicated. But then what we did an optimization where we found that when we did an optimal trajectory, it never needed any thrust. In fact, it only used drag for the entry, just like the Apollo capsules or many other entry vehicles would use. So then we realized that all we really needed was the engines at subsonic speeds, and that's how we changed our design. So Annie, in the midst of it, had to go from ramjet propulsion to turboprops or ducted fans. This gives you an idea of the aerodynamic work we did on it. It shows the flow field. As I mentioned, we started with the ramjet, went to propellers, and you can see the design iterations till we finally converge on the design. And we use NASA aircraft code. This is freely available to anybody who wants to use it. It's really nice stuff. So talk more about the fusion reactor, which is one of the more interesting parts. Again, it was developed by Dr. Sam Cohen at Plasma Physics Lab. He worked on ITER for many years and decided to switch to this. It uses a different fuel than ITER would use. It used deuterium helium-3. And why do we use that? Because the deuterium helium-3 reaction produces only ions, no neutrons. Neutrons tend to destroy your engine. If for a DT machine, most of the energy is in neutrons, and they're so high energy they destroy everything. And there are no materials right now that can withstand that bombardment. People are working on it and hopefully making progress. So we chose deuterium helium-3. Now you might say, well, wait a second, Mike. If you have deuterium, isn't it going to fuse with other deuterium? And you'd be absolutely right. And that does produce tritium and neutrons as side reactions. However, the neutrons themselves are not quite as high energy as the ones for DT. So they're not as big a problem. And fairly conventional materials could last 10 to 20 years. But one of the things you need for D-helium-3 fusion is much higher fusion temperatures. So I'm going to use electron volts as my measure. And what for this you would need for a DT machine, which is what Tokamac's doing, what our friends at Commonwealth Fusion are doing, maybe you can get by with 5 kilo electron volts, probably 10 or 20. We need about 100. So that's much hotter. However, we have a very interesting thing about our configuration of our magnetic fields is high beta. Beta is the ratio of pressure to magnetic pressure. So a low beta machine means you get very little pressure for a lot of magnetic pressure. You need big coils. And those machines tend to be very big, like a tokamak. For ours, the beta is close to 1. A tokamak might be 0.02, for example. And so we can make a much more compact machine, and this leads itself to compact applications. So on this slide, I told you some of the nice features, but an interesting thing is the nature of it, because remember those side reactions I talked about? That tritium, we don't want that to fuse with deuterium, then we're back to our high energy neutron problem. It has to leave the reactor. So we can't have it have a big radius. It has to be small. And that limits us to maybe, a half megawatt to 10 megawatt size. This is what the whole thing looks like. And these are all the subsystems. So we have superconducting coils, probably high temperature. We have to cool them. That's a subsystem. There's the fuel. You have to store the fuel. Storing these cryogenic fuels for long periods of time is a very hard problem. NASA and other people are working on it because deuterium and hydrogen just want to leak out of everything. So that's a challenge. Our machine is a driven machine. And a driven machine is one in which the heating is done, in this case, by an RF generator. It's very much like an induction motor. But that's how we heat the plasma. The products of the reaction do not heat the plasma. In a big DT tokamak like ITER, the products produce or supply a lot of the energy for heating. We can't do that. So we have to recirculate waste energy to heat the plasma. Now, another thing about that high temperature I mentioned, at those high temperatures, if the electrons are those temperatures, they produce a lot of X-rays. So we have to recycle all that energy. And we have an X-ray absorber, we have a Brayton cycle or combined cycle engine to convert that into electricity. And then this whole thing has to work. And of course, the power balance has to work. And we've shown that it does work. One of the important things is that you do have radiators, as I showed, and it's important to include that in your roll-up of your mass, because otherwise you end up with unrealistically optimistic numbers. So again, here is a summary. I'm not going to read through this, but let's look at a couple of key things. Bottom is the specific power. That's a critical parameter. That's how many kilowatts you get per kilogram. Notice nuclear electric. That might be like JIMO. These are being proposed now. The problem is, one, is that fission reactors tend to be not very hot because otherwise they destroy themselves. And then you have to have a lot of power electronics to convert it into a form you can use in electric propulsion. So you get really low specific powers. Solar power is actually better. Of course, you have to be in the inner solar system, within the orbit of Mars. Otherwise, you end up, because of this square law of decrease in solar flux, it ends up being impractical for, say, going to Saturn. Direct fusion drive our best estimates say a half kilowatt per kilogram, maybe 2 kilowatts per kilogram, maybe more. It really depends on the shielding we need, the superconducting coils, because we still need shielding because we still have neutrons and we have X-rays and things like that. On the left, there's the beta parameter I told you about, and these are the different values. As in tokamak, which is a really amazing machine. I visited a couple of years ago. It's an incredible experiment, but it's very low, so it needs an enormous machine. There are some concepts that use the tokamak for spaceflight, and there's a paper I wrote with Zakharov and Gorlienkov at Plasma Physics on how you might do that, but it's an enormous rocket engine. FRC gets 0.8, which means we can make it small. So you have to do a lot of analysis and numerical. So one of the things we have to do is, well, remember I mentioned that we get charged particles, which is great because we can direct them out of magnetic nozzle, but their velocity is very, very high. And it turns out for any mission, you say, I want to get to Saturn in this amount of time, and this is my specific power. There will be an optimal exhaust velocity, and it's much lower, maybe 200 kilometers per second than the product. So what you have to do is mix it with additional hydrogen or deuterium. And so we use UEdge, which is actually a tokamak, basically an MHD code, to show how it would work. And you got some interesting results. It turned out that there is a minimum amount of this additional gas you have to add and a maximum. So it means for example, you couldn't go to a very low exhaust velocity and really high thrust. You're limited. I haven't written this down, but there's a very important equation which relates exhaust velocity and thrust to power. So power equals 1/2 times thrust times exhaust velocity divided by the power conversion efficiency. So you would think, hey, I can trade exhaust velocity versus thrust, and you can do it to a degree, but you don't have infinite flexibility. And that's what this chart shows. So this gives you two very important things. And anybody who writes a paper on fusion, you want to look for this. One is the mass breakdown. And let's look at it a bit. You can see shielding is pretty big. And then you can see the magnets are pretty big. The structure, you have the magnets produce huge forces, and you have to have enough structure to keep them from collapsing. And the power conversion is fairly big. So this is how we've broken up. So that's why we get our specific power numbers from. And on the right, you see the power flow. It's very important that you account for where the power goes. Now, an interesting thing is the RMF power, that's the power we're using to drive the reaction, is a lot harder than you would expect. You say, wait a second. Just to even get the little amount of fusion fuel up to fusion temperatures, that's like kilowatts. But what we actually are supporting is the X-rays coming out of it. So essentially, that RMF power is going into both heating the plasma and essentially compensating for the X-rays that are coming out. That's why you need so much power. It's an interesting point, and you have to understand that, because otherwise you come up with ridiculously optimistic numbers. Because hey, I only need 20 kilowatts of heating, when you don't. You need a lot more. So the conclusions are, this vehicle would allow you to explore Titan for months and years. You don't need that much fuel. Obviously, there's reliability factors and things like that. And you could explore the whole surface. And you would have a lot of power for scientific experiments. You could carry a mini submarine, laser drills, all sorts of things. And the transfer would also be by a fusion-powered rocket engine. This would take you from low Earth orbit all the way to Saturn and then to Titan, and would stay in orbit and act like a relay. In the future, it could actually bring people, because again, one of the advantages of fusion propulsion is you get places a lot faster than you can, say, with a Hohmann transfer or with a bunch of gravity flybys. And the next step is to build a test machine. Right now, our machine has very low magnetic field, so we don't get much heating. And that's the physics. The numbers we get are exactly what we expect. Unfortunately, our machine is so old that we really can't upgrade it too much. The next machine would have 1 Tesla coils. Now, that's not what an operational machine would have, but it's a good intermediate step, because by going into an intermediate step, we can study the physics, understand them before we try to build something bigger. If we could build you could build the big machine now. The coils we're using are found in an MRI machine that you find in any hospital. But if you built the big machine first, it'd be like Robert Goddard trying to make the engines for the Saturn V rocket. You don't want to make that big a jump in one fell swoop. And so the next one would be a 5 to 7 Tesla machine. We have a proposal to maybe fly it. So it would produce some fusion power, though most of the thrust would come from other energy sources. But it'd be a great next step. And that's me. Though anybody wants to send me emails with questions, they're welcome to do so. And I'm happy to answer questions.
Thank you, everyone, for attending, and thank you to our presenter. Are there any questions? Doesn't seem to be any questions. Maybe if you think them afterward, you can write, oh, great presentation from Steve Arnold. Okay. So if there are no questions, you can write later to the professor. And yeah, thank you for being here. This is a moment for a short break before we have our next session. And keep enjoying the conference. Take care. Thank you, Professor.
Thank you. Have a great day. Bye, everybody.
Bye. Very interesting topic. We have really informative, great presentation. Just praises.
I know, I saw the comments. Thank you so much for your really kind comments, everybody. And as I said, you can email me. I hope you all get my email address and send me any questions you have. I also have the full paper. It's actually published in Acta Astronautica, so you can get that through them. But I can also send you a copy if you'd like.
Awesome. And we'll post, the conference will be stored in the PSO platform in case you want to listen to it again. Oh, there's a question.
Oh, I actually don't know the answer to the question. It's very interesting. And I will see if I can find you some references to look at that. That's an interesting point.
Okay, great. So again, enjoy the conference. Thank you, Professor, and have a great day.
You too. Thanks so much, Anna. It was wonderful.